Okay, so we are now going to prove this theorem 271, where in fact we ended the last video. So in this theorem we are given two groups G and G bar, and there is a homomorphism phi from G onto G bar. Okay, the homomorphism is surjective, it's onto G bar, and the kernel of this homomorphism is K, which let us recall is the set of those elements in G that are mapped by phi onto the identity element of G bar. And we already know that the kernel is a normal subgroup of the domain group G. So we can form this quotient G by K, it makes sense. We then have to prove that this quotient group is actually isomorphic to G bar. So let us see how we can prove this. The proof is direct. We are going to define a map and we will prove that it's an isomorphism of G by K onto G bar. So the map is defined like this. Define a map psi from G by K to G bar by psi of an element in G by K will be a right coset of, in fact a coset of K, right or left, it does not matter since K is a normal subgroup. So every right coset is the same as the corresponding left coset. We will map this coset onto the element phi of x. Let us first see whether this makes sense. In this coset Kx, x has to come from G. On that, if we apply the map phi, then we are going to get an element of G bar because phi maps G onto G bar. So at least this is a function from G by K into G bar. We now have to verify that this function is in fact well defined, that equal inputs give us equal outputs. So we are not going to mention that this in fact is a function from G by K to G bar, that is understood. So let Kg, we can take x and y also. Let Kx and Ky be two elements in the domain such that they are equal. Okay, we are going to prove that the function is well defined, not that the function is one to one. Okay, so the elements are equal. Then from properties of cosets, this will imply x y inverse belongs to K, which in turn implies that because K is the kernel of phi, so the phi image of this element will be equal to E bar, where E bar is the identity in G bar. Okay, now we are going to use the fact that phi is in fact a homomorphism. Since phi is a homomorphism, phi of x y inverse is equal to phi of x, phi of y inverse, and that is equal to phi of x, phi of y inverse. Okay, we are using elementary properties of a homomorphism. Hence phi x phi y inverse equal to phi of x y inverse equal to E bar, or phi x is equal to phi of y. But phi x, according to our definition of psi, is psi of kx and phi y is psi of ky. So psi of kx is equal to psi of ky. So equal inputs give us equal outputs. So that means the function is well defined. Thus psi is well defined. Next we are going to prove that psi is in fact a homomorphism, because these are two groups, so it makes sense to verify whether psi is a homomorphism. So let us take two elements, say kg1 and kg2, belonging to the quotient group. Then what is the psi image of kg1 kg2, where the product kg1 kg2 is being carried out in the quotient group? So it will be k g1 g2, and according to our definition of psi, this is phi of g1 g2. Now we already know that phi is a homomorphism, so this is going to be phi of g1 phi of g2. I hope it is visible. Okay, phi g1 phi g2. So this ultimately becomes psi of kg1 psi of kg2. So psi is a homomorphism. Okay. The next thing we are going to verify is that psi is onto, it is surjective. So let us take an arbitrary element in G. In G bar. Let G bar be any element in G bar. Now we are going to use the fact that the mapping phi is onto, and it's from G onto G bar. Since phi is onto, there exists an element G in G such that phi of G is equal to G bar. But then we are almost there. But then kg belongs to the quotient group G by K such that psi of kg is equal to phi of G, which is equal to G bar. So that means for the element G bar, in G bar we have found an inverse image kg in G by K under psi. Hence psi is onto. is onto. We have thus proved that the map psi is a well-defined homomorphism of G by K onto G bar. So the only thing left for us to prove, to show that psi is an isomorphism, is that psi is a one-to-one map. So for that we are going to show that the kernel of psi consists of only the identity element in the domain group, that is G by K. So let us just summarize here. We have thus shown that psi is a, there is no need to in fact write it's well defined, because if it is not well defined there is no point working with it. Psi is a homomorphism of G by K onto G bar. We shall now show that the kernel K psi of psi consists of the identity element K of G by K. That is, we are going to show that K psi is the trivial subgroup of G by K consisting of only its identity element. But let me just put some ink first. I wasn't able to film any video this last 2 days because of Diwali celebrations and the firecrackers associated with this festival. I have nothing against the festival, but I was just not able to do it. It was that loud. Okay, so we are now going to show this. So keep in mind that K psi, being the kernel of psi, is first of all a subset of the quotient group G by K. So any element in it will be a coset of K in G. So let us take an element K, okay, Kx belonging to K psi. Then, because Kx belongs to the kernel of psi, its psi image must be the identity element. But where? Which identity element? Identity element in G bar. Keep in mind that psi is a map from G by K into G bar. Okay, so then E bar, which is the identity element of G bar, is equal to psi of Kx. But according to our definition of psi, this is equal to what? Phi of x. Now, what does this tell us? This tells us that x belongs to the kernel of phi, because phi is a map from G onto G bar, and here we are getting the identity element of G bar. So which implies x belongs to the kernel of phi, which is K, Hence, but if x belongs to K, because K is a subgroup of G after all, so the coset Kx will be equal to K. Thus, Kx was an arbitrarily chosen element of K psi, so it has turned out to be equal to K. Thus, K psi is contained in K. And the reverse inclusion, of course, is obvious, because we know that the kernel K psi is a subgroup of G by K, and this is the trivial group which is contained in every subgroup. Of course, we also have this. So by a previous result, we know that when the kernel of a homomorphism is the trivial group, then the homomorphism is 1 to 1, and conversely also. This implies psi is 1 to 1. So that means psi is a 1 to 1 homomorphism of G by K onto G bar, or in other words, psi is an isomorphism of G by K onto G bar. Psi is 1 to 1. Thus, psi is an isomorphism of G by K onto G bar. This proves our thing which we were claiming. G by K is isomorphic to G, that is, group theoretically there is no distinction between G by K and G bar. They are one and the same, only their elements have been labeled differently. We have already discussed about this in the previous video. Now, after this, there are some words from the author which are important. We have also talked about it a little, but let's just write it properly, what the author has written. Theorem 271 is important. And the reason is this. For it tells us precisely what groups can be expected to arise as homomorphic images of a given group. These must be expressible in the form G by K, where K is a normal subgroup. In fact, we can write, okay, K, fine. K is a normal subgroup of G. Conversely, there is a converse also. We have already come across the converse even before this theorem, which is the thing where we are given a group and a normal subgroup. Then we prove that there is a homomorphism from the group onto the quotient group formed by the normal subgroup. Conversely, by lemma lemma 271, for any normal subgroup n of G, the quotient group G by n is a homomorphic image of G, because we have proved that there is a homomorphism from G onto G by n, where every element in G is mapped onto the coset of n formed by that element. For example, x is mapped onto nx. So these two results together excuse me, these two results together tell us that there is a one-to-one correspondence between homomorphic images of a group and normal subgroups of the group. Excuse me. Just give me a moment. Is a homomorphic image of G. Thus, there is a one-to-one correspondence between the homomorphic images of a group and the normal subgroups of the group. And in fact, this theorem, this one, shows us that in order to find the homomorphic images of a group, we in fact need not leave the group at all. So what you do, you have the group G, you find all of its normal subgroups, say n1, n2, n3, etc. It will have a number of normal subgroups. Every group has at least two normal subgroups, namely the trivial group consisting of only the identity element and the group itself. Besides these two, there may be more or there may not be more. Whatever the case may be, you collect all the normal subgroups, and then what you do, you form these quotients by lemma 271. All of these are homomorphic images of G. Is there any other homomorphic image that is not accounted for in this list. This theorem says that no, there cannot be any other homomorphic image, because if you have a homomorphic image, say from G to G bar, there is an onto homomorphism, so that G bar is a homomorphic image, then essentially G bar is actually of the form G by K, that is, it's isomorphic to G by K, where K is the kernel of this homomorphism phi. But since the kernel is a normal subgroup, so in this list of all such quotient groups, we have in fact considered G bar up to isomorphism, of course. So that's why in order to find all the homomorphic images, this list of quotients actually it has all the homomorphic images. And Herstein writes like this. If one were to seek all the homomorphic images of a group, say G, one could do it by never leaving G. As follows. Find all normal subgroups N of G and form all the quotients G by N. These are all the homomorphic images of G up to isomorphism. Up to isomorphism, that is written. In fact, we have already said that there is no real distinction between two groups that are isomorphic. So they are treated as equal. Okay, so now the question, another question now arises. Okay, fine. So we can find all the homomorphic images by simply forming quotients by all the available normal subgroups. Now, so the thing now comes down to the collection of all normal subgroups of a group. What is the easiest possible case that can arise? Namely, that case where a group G has only two normal subgroups, itself and the trivial group consisting of the identity element. These types of groups have a name. They are called simple groups, precisely because they have exactly two homomorphic images corresponding to those two normal subgroups. One of them is this and the other is this. This corresponds, in fact, this is isomorphic to the group G itself, and this is isomorphic to the trivial group. if you really think about it, you can see that these are the only two homomorphic images of such a group. So the next thing is simple groups. We are not going to see any theory of simple groups in this book, but just the definition has been given. A group is said to be simple if it has no non-trivial homomorphic images. Or correspondingly no non-trivial normal subgroup. That is, no non-trivial normal subgroup. Note that in a simple group there may be non-trivial subgroups. A simple group does not have a non-trivial normal subgroup. Okay, don't forget about this normality. If in a group G the only subgroups, we are not talking about normality now, if the only subgroups are E and G, then that type of groups, we have in fact solved one exercise regarding the nature of such groups, and we proved that in such groups, such groups must be cyclic groups of prime order. They must be finite first of all, and they must be cyclic, and they must have prime order. Here, however, is in a simple groups of course need not be of prime order, but they should have, or they must have, only two non-trivial normal subgroup. Okay, there may be other subgroups also which are not normal, but they are non-trivial. A famous long-standing conjecture was that a non-abelian simple group of finite order has an even number of elements. That means the conjecture was that if you have a finite simple group which is non-abelian, then it must have an even number of elements. There is no such group with an odd order. This was proved by the two American mathematicians Thomson and Fate. They are famous for classifying simple groups finite simple groups. Classifying means they have given a list of all possible simple groups, so that finite simple groups, so that if you take any simple group, if you find any simple group that is finite, then that will be isomorphic to something from that list. I think it is finite simple group if I am remembering correctly. And John Thomson. Okay. Now we have discussed previously that when we form a quotient group of a group by a normal subgroup, what we do is that we collapse things. Say this is our group G and there is a normal subgroup. So when we form the group G by N, we collapse all the elements in N and think of it as a single element in G by N, that is N, and it turns out to be the identity element. It's like we have identified all the elements in N and we are treating them as one object. Correspondingly, in other places also there are collapses, namely the cosets of N. So the elements, some elements are treated as one. Now that means when we form G by N and when we are in the group G by N, we lose some sort of information about G. Because we are treating elements of N, all the elements of N as a single object. We are not bothered about any intricate relationship that they may have among themselves. We are only bothered about the structure of the group G by N. So although we are losing some amount of information, often enough remains that we can still say something about G from the structure of G by N. And in fact, we are now going to look at two applications of the ideas and results we have come across in this section so far. And these applications are non-trivial, that is, each one of them says something about a group that is not immediately apparent. So let us see what we mean by these remarks. The applications are of course two results. The first one is Cauchy's theorem for abelian groups and the second one is the Sylow's theorem for abelian groups. So it's given also like that, application 1. Cauchy's theorem for abelian groups. Okay, the statement of this theorem is this: let G be an abelian group of finite order, actually I could have written finite abelian group. I think that's how it's written in the text. Okay, fine. Of finite order of G and P divides order of G, where P is a prime. Then there exists an element A that is different from the identity element in G such that the pth power of a to the power p is equal to the identity element of G. Okay, let us now see the proof. We shall prove this theorem, or result, in fact, since we are not calling it a theorem, prove this result by induction on the order of G. Okay, so the base case, of course, is the case where G has only one element. When order of G is equal to 1, the result is, strictly speaking, we should not call it a result before proving it. It becomes a result only after the proof is complete. But you can understand, instead we can call claim. Okay, something we are claiming to be true, then after we prove it, then it becomes a result. The result is, you can, so you should understand that the sense in which this word is being used here is that it is something that is going to be proved and it will be proved. Okay, so the result is vacuously true. Let us pause to understand why this is so. You see, when order of G is 1, then this statement is false. P dividing 1 is false. No prime divides 1. And our result is what? Our claim is, after all, an implication. If G is a finite group and P divides order of G, then something happens. That means this is the hypothesis, and we have a conclusion that there is a non-identity element whose pth power is identity, so and so. So here the hypothesis is false. So that means the implication is vacuously true. So that's why we are saying that when order of G is 1, the result is vacuously true. And this is the basis for our induction. Now we will write an induction hypothesis, and then we will try to carry out the induction step. Now assume that the result is true for all abelian groups having order less than n, orders less than n, where n is some positive integer. So here we are in fact using the strong principle of induction, and let G be an abelian group such that order of G is equal to n. Okay, now our aim is to show that there is such an element whose pth power is equal to the identity in G. If G has no subgroup other than the trivial group and this group and G, then G is cyclic of prime order. It's that exercise. And in fact, let us just mention by exercise 3 that is there after section 2.5, that is after that section named a counting principle. Okay, then in this case G is cyclic and is of prime order, but according to our hypothesis we keep in mind that we don't just have an abelian group G of order n, but this is still there in the background, that P is a prime that divides order of G. Now since G itself has a prime order, that prime must be equal to this prime. It cannot be any other prime. Since P divides order of G, we must have order of G equal to P. Okay, so in such a group there will be P elements, one of them will be identity and there will be P minus 1 non-identity elements, and all of them will have their pth powers equal to the identity by the second corollary to Lagrange's theorem, which says that if you take an element A from a group G that is finite, then this power equals the identity. Okay, so in this case we are done. In this case there are P minus 1 non-identity elements. There are P minus 1 non-identity elements in G whose pth should we write like this, or in fact elements A in G such that A to the power P is equal to E. We need only one, but we have got P minus 1 for in this particular case. So this is when G has no subgroup other than these two. So now next we have to assume that there is in fact a subgroup. Now assume that G has a subgroup H different from both E and G. Okay. If it happens that the prime P divides order of H, it may or may not happen. In the case when it happens, then since order of H is strictly less than the order of G, this is because G is not equal to H. So we can then apply the induction hypothesis on H because it has a smaller order than N. So the induction hypothesis gives us an element A not equal to E in H such that A to the power P is equal to E. But since H is a subgroup of G, so this element is in G also. But then we have found an element A not equal to E in G such that A to the power P is equal to E. If it happens that P divides order of H. So next we have to consider the case where P does not divide order of H. Next, assume P does not divide order of H, but because P is a prime, so if P does not divide order of H, then P and order of H are relatively prime, that is their greatest common divisor is 1. And why is that so? It's because the only positive divisors of a prime are 1 and the prime itself. Among them, P does not divide order of H means P cannot be a common divisor of P and order of H. The only other divisor left is 1. So the only positive common divisor of P and order of H is 1. So that will be the greatest common divisor. Then the GCD of P and order of H. Recall that the GCD of two integers in Herstein's book is denoted by this symbol. This is equal to 1. Now, consider the quotient G by H. The question is, can it be considered? Yes, you can consider it because keep in mind that G is an abelian group. So H is automatically normal. So this quotient can be considered. Since order of this quotient group is order of G divided by order of H, we have P dividing order of G by H. What is happening here? Why are we able to conclude this? You see, since it's already given to us that P divides order of G, so this can be written like this: P times K divided by order of H, where K is some positive integer. Now P and order of H are relatively prime, and we know that this is a positive integer because it is the order of this quotient group. So that means we must have division here with zero remainder. Order of H does not divide P, so that means order of H must divide K, where we are using that result which says that, say, A, B and C are three integers where A divides BC and A and B are relatively prime. Then this implies A divides C. Order of H divides PK, and P and order of H are relatively prime, so order of H must divide K. So that means this quotient is actually an integer, K divided by order of H, because of this divisibility relation, which implies the order of this quotient group G by H is an integer multiple of P, and that's why P divides order of G by H. Okay, now what is it that we have? Note that G by H is itself an abelian group and P is dividing its order. Now what is the relationship between this order and order of G? It will be strictly less than the order of G, since order of G by H is less than the order of G, and that is happening because of this. You multiply both sides of this inequality by order of G and then divide both sides by order of H, you get this one. And why is this true? That this is because H is not equal to the trivial group consisting of only the identity element. H has something besides the identity element. So because this is true, so now we can apply the induction hypothesis on the group G by H. The induction hypothesis implies there exists an element, but where? Element in G by H that is not equal to the identity element of G by H and whose pth power is the identity element of G by H. So that means it is going to be a coset of H that is not equal to the identity element of G by H in G by H such that its pth power is the identity element of G by H. Although it looks something like we have things like things that we haven't seen, but it's just simply this. Okay, in place of A we have HG here, in place of E we have H, and the other things are also like that. Okay, now what do these conditions tell us? The first one tells us that G does not belong to H, and the second one tells us that G to the power P belongs to H. Okay, now note that since G to the power P belongs to H and H is a subgroup of G, so by the second corollary to Lagrange's theorem, if we raise this to the power order of H, then we have to get the identity element of G. This implies okay, C corollary to Lagrange's theorem. I don't remember the exact number of the theorem, so I'm just calling it Lagrange's theorem. You know what the theorem is. That is, using the rules of exponent, we can alter the things slightly and write this. Now we are almost there. We have in fact found an element in, because this is after all an element in G to the power order of H, whose pth power is equal to E. But additionally, we also need to make sure that this itself is not equal to E. So let's suppose just that. Suppose G to the power order of H is equal to E. Then Hg to the power order of H is equal to this, which is equal to He, that is equal to H. Now look at these two equations. Hg to the power order of H is equal to H, and at the same time Hg to the power P is also equal to H, and we know that P and order of H are relatively prime. Since P and order of H are co-prime or relatively prime, there exist integers, say alpha and beta, such that P alpha plus order of H times beta is equal to 1. Now let us see how all these things can be used to arrive at a contradiction. Okay, now Hg can be written like this. hg to the power 1. Now in place of 1 we can write p alpha plus order of h times beta. Now you use the rules of exponent in the group g by k, because this calculation involves cosets and their products. So we are in the quotient group g by k, g by h. Okay, so there we use the rules of exponent and write this product like this. Alpha, it does not matter what sort of integers alpha and beta are, they may be positive, negative or 0, each one of them. The only thing that matters is that they are integers, times hg to the power order of h to the power beta. So this is equal to h and this is also equal to h, and keeping in mind that h is the identity element in the quotient group g by h, we ultimately get h. And this is a contradiction because now we have hg equal to h, but hg is not equal to h. A contradiction. So our last supposition is wrong. That is, we must have this not equal to identity. We have thus found an element A, which is g to the power order of h in G, such that A is not equal to identity. We have just now proved this, and the pth power of A is equal to the identity, which comes from here. So this completes the induction, or we should write that. I almost forgot that we were doing an induction proof. This completes the induction and proves the result. Okay. And the second application is Sylow's theorem for abelian groups. So here it is, but first some ink. Application 2. Sylow's theorem for abelian groups. Okay, here the statement is this: let G be a finite abelian group and okay, not like that. Let G be a finite abelian group. Let P be a prime and alpha be a non-negative integer. Such that the pth power, the alpha power of p to the power alpha divides order of G, but p to the power alpha plus 1 does not divide order of G. So you can say that p to the power alpha is the largest power of p that divides the order of the group. Then G has a subgroup of order p to the power alpha. So this is Sylow's theorem for abelian group. This is true in general for any group, okay, not just abelian. Just like that, Cauchy's theorem is also true for non-abelian groups, but we are in a position to prove these results for abelian groups at this stage. So that's why we are having these applications. Okay, so let us see the proof here. If alpha is equal to 0, then the subgroup E of G can be considered which has order p to the power 0. You see, when alpha is equal to 0, the hypothesis says that 1 divides order of G, but p does not divide order of G. And B, in that case, we are claiming, the conclusion says that G has a subgroup of order p to the power 0, which is 1, and of course there is a subgroup of G of order 1, namely the trivial subgroup. Now, so this is one case. Now assume that alpha is greater than 0. Then this part of the hypothesis tells us that P in fact divides order of G. Of course, p to the power alpha divides order of G, but in particular P also divides order of G. Then P divides order of G. So by Cauchy's theorem for abelian groups, there is a non-identity element in G whose pth power is the identity. Then by application 1, G has an element A not equal to E such that A to the power P is equal to E. Just like the previous one, we cannot say exactly like the previous one. In this case, we are going to produce the actual subgroup. We are now going to define a subset of G, prove that it's a subgroup of G, and then we will prove that it has this desired order, p to the power alpha. Define the subset S. Okay, let us denote the subset by S. It is the set of those elements in G for which x to the power p to the power n is equal to identity, where n is some non-negative integer depending on x. That means if you have an element of G for which you find a non-negative integer n such that this power becomes equal to e, then such an element will belong to S, and S is in fact the set of such elements. Now our first thing we aim to do is we want to prove that S is a subgroup of G. Since e to the power p to the power 0, you can in fact take in any value of n in this case is equal to e, we have E belonging to S. So S is a non-empty subset of G. Thus, okay, now we want to show that S is a subgroup of G. Since we are in a finite group, it's enough for us to show that S is closed under the operation in G. You try to recall that thing where if you are in a finite group, then in order to show that a non-empty subset is a subgroup, it's enough to show that it's closed. That's it. You don't have to bother about inverses. They are automatically there inside the set. So let x and y be two elements in S. Then there exist non-negative integers n and m such that x to the power p to the power n is equal to e and y to the power p to the power m is equal to e. That because that's the condition for being in S. Since G is abelian, we have x, y whole to the power p to the power n plus m. From abelianness of G, we can write the power like this. And then using one of the rules of exponent, it can be written like this times y to the power p to the power m whole to the power p to the power n. Okay, now this is E and this one is also E, so we get E. This implies xy belongs to S. Okay, note one more thing, that because n and m are non-negative integers, n plus m is also a non-negative integer. That also should be clear. Thus, S is a subgroup of G. We now want to show that its order, the order of S, is p to the power alpha. The first thing to show in that direction is that p is the only prime divisor of the order of S, and we will show this by supposing that there is some other prime that divides order of S and arrive at a contradiction. Now we claim that order of S is equal to p to the power alpha. Suppose there exists a prime q not equal to p such that q divides order of S. Then we can apply application 1. Then by application 1, there is an element b not equal to E. In S such that means we are applying Cauchy's theorem for abelian group on the group S, such that b to the power q is equal to E. But b belonging to S, because b is an element in S, also implies, from the definition of S, b to the power p to the power, what should we take? Let us take u equal to E for some non-negative integer u. Okay, now note that in the integer p to the power u, the only prime divisor is p, and in the integer q, of course, the only prime divisor is q, and they are different. So the numbers, the integers q and p to the power u are relatively prime. Since q is not equal to p, the GCD of q and p to the power u is equal to 1. Hence, there exist integers, say gamma and delta, such that q gamma plus p to the power u delta is equal to 1. Now we can write one more line here. Okay, now we are going to use this. I think you can almost guess what we are going to do, because we have done a similar thing before in the previous proof. We have this relation, this relation, this relation, and this relation. They will all taken together, they will give us a contradiction. Now b is equal to b to the power 1, which is b to the power q gamma plus p to the power u delta, and let me write it there. This is equal to b to the power q whole to the power gamma times b to the power p to the power u whole to the power delta. Equal to e. So this is a contradiction because b is originally not equal to e. So our last supposition is wrong, that is, there is no such q. This implies order of S is equal to alpha, beta, gamma, delta, epsilon, p to the power epsilon, where epsilon is greater than 0 and less than or equal to alpha. Now what is happening here? Okay, fine. There is no prime divisor of the order of S other than p, so that means the order of S will be a power of p. It cannot be anything else. But how are we able to conclude something about this exponent epsilon? Note that since A belongs to S and A is not equal to E, we have forgotten about this piece of information. You go towards the beginning of the proof. There, after assuming that alpha is greater than 0 and correspondingly after ascertaining that p divides order of S, no? Order of S or order of G? It is order of G. Okay, I was right. It is order of G. We then applied application 1 to have an element A not equal to E in G such that A to the power P is equal to E. So this is us applying application 1 on G. Now you look at this equation. This is A to the power P to the power 1 being equal to E. So from the definition of the set S, A must belong to S. That's why we have written this. And since A is not equal to E, that means S has an element other than the identity. So epsilon cannot be equal to 0. because if epsilon is 0, then order of S is 1, which is not the case. S has something else, besides identity, it has something else. So that's why we have 0 less than epsilon. Epsilon is a positive integer, and by Lagrange's theorem, since p to the power alpha has to divide, p to the power epsilon has to divide p to the power alpha, so epsilon must be less than or equal to alpha. We have epsilon greater than 0. Also, since by Lagrange's theorem, order of S must divide order of G, we have epsilon less than or equal to alpha. Okay. Our aim now is to show that epsilon is actually equal to alpha. Suppose it is not. Suppose epsilon is strictly less than alpha. Consider the quotient G by S. Okay. Since order of G by S is equal to order of G divided by order of S, which after calculation gives us alpha minus epsilon. So you can see that since alpha is greater than epsilon, so this number is divisible by p. Order of G by S. Thus, again, do you see how many times we are using application 1? There is an element Sx not equal to S in G by S such that Sx to the power p is equal to S. Now, Sx to the power p is equal to S. This implies Sx to the power p equal to S, and hence x to the power p belongs to S. But for an element to be in S, that element to the power p to the power some non-negative integer should be equal to identity. But then p to the power k is equal to identity for some non-negative integer k. Thus, using the rules of exponent, this is equal to identity. But then k plus 1 is also a non-negative integer, which implies x belongs to S, and so Sx is equal to S, contradicting this one. So our last supposition is wrong, that is we must have epsilon equal to alpha. Thus order of S is actually equal to p to the power alpha. This way we have really found constructed a subgroup of G of order p to the power alpha. Okay. Now to strengthen this application, to say something more about this second application, we are now going to show that this subgroup is in fact unique. Okay, there is only one such subgroup. There cannot be two different subgroups of G of this order. Suppose G has another subgroup T not equal to S of order p to the power alpha. Since G is abelian, so Ts is equal to St, and hence Ts is a subgroup of G. Now what is the order of Ts? Order of Ts by that counting principle is equal to order of T times order of S divided by order of T intersection S, which is equal to p to the power alpha, because both these subgroups are of order p to the power alpha, divided by p to the power say gamma, where order of T intersection S is p to the power gamma. And why is it of the form p to the power gamma? It's because T intersection S is a subgroup of both T and S, and each one of them has this order. So the order of T intersection S has to divide this, so it will be some power of P, and that too this gamma must be less than or equal to alpha. Note that since T intersection S is a subgroup of say S, or we just write like this. Note that T intersection S is a subgroup of S, and that's why we have this. Now gamma naturally is a non-negative integer, and it is less than or equal to alpha because it has to divide the order of T as well as the order of S same. So that's why by Lagrange's theorem gamma has to be less than or equal to alpha. If gamma is equal to alpha, then order of S intersection T is equal to order of S, because then both will be equal to p to the power alpha, but this would imply that S intersection T is equal to S. Why? Because you see, S intersection T being a subset of S is contained in S. In that case, if they happen to have the same number of elements, both of them are finite, then they must be equal. This would in turn imply that S is a subset of T. And similarly, if you consider the other equation where you have T here, thus S will be equal to T, which contradicts this. So we must have gamma less than alpha, but then order of Ts, which is this, p to the power 2 alpha minus gamma, which can be written like this, alpha plus alpha minus gamma, is greater than p to the power alpha plus 1, not greater than or equal to. You see, because alpha is an integer, a positive integer greater than gamma, so alpha minus gamma is at least 1. So that's why we have this, and this contradicts the hypothesis that p to the power alpha plus 1 does not divide order of G, but Ts being a subgroup of G must divide order of G. Its order should divide order of G. So its order is at least p to the power alpha plus 1. So it has to divide order of G, so which is a direct contradiction. So that's why this supposition is wrong. So our supposition that G has at least two distinct subgroups of order p to the power alpha is wrong. So the subgroup of order p to the power alpha, that whose existence is guaranteed by application 2, is also unique. Now note that although we are saying in advance we are saying that both Cauchy's theorem as well as Sylow's theorem are true for non-abelian groups, but this uniqueness is not carried over to non-abelian groups. If you look at the group S3, our symmetric group of degree 3, we know that its order is 6, which is 2 times 3. So that means 2 is a prime that divides order of S3, and 2 square does not divide order of S3. So by application 2, S3 must have at least one subgroup of order 2 to the power 1. In this case alpha is 1. But In fact, it has more than one subgroup. These are 3 different subgroups of S3 of order 2. Okay, so the uniqueness is not carried over to non-abelian groups, but existence of course is there, and we are going to we will eventually prove these results, these applications for all groups, not just abelian groups. So with this I end the video here. After this we will go back to the general result. There are 2 more results, one correspondence theorem and another one theorem. Then the the section will end, then we will move on to the exercises. Okay, so that will be all in group theory in this video. So this is me, Lucifer, from a mathematical room. Have a nice day.